Hello everyone. Today we are presenting a new architecture designed to solve a fundamental inefficiency in large language models. We call it memory layers at scale. Our goal is simple: to decouple the capacity of a model from its compute cost, allowing us to build systems that know much more, without costing much more to run. To understand why we built this, look at the graph on the left. This is the scaling paradox. In standard dense transformers, knowledge is encoded directly into the model weights. If you want the model to memorize more facts, like birthdays or capital cities, you have to make the model larger. But making the model larger increases the compute cost linearly. You end up burning massive amounts of energy on complex matrix multiplications just to retrieve a simple static fact. We want the graph on the right, a flat compute cost, even as we add billions of parameters of memory. So, how do we achieve that? By changing the anatomy of the layer. Instead of a dense matrix where every input touches every weight, we use a sparse memory layer. Think of this as a massive key-value store. When a token comes in, that's our query queue, we don't activate the whole layer. We simply perform a lookup to find the top k most relevant keys. We only activate a tiny fraction of the parameters. This makes the operation computationally cheap, but storage-rich. Now, you might ask, if you have millions of keys, doesn't searching through them slow everything down? That is the retrieval bottleneck. If we did a naive search, it would be too slow. Our solution is product keys. We construct a massive virtual key space by taking the Cartesian product of two much smaller sets of subkeys. This reduces the search complexity from linear to square root. It allows us to efficiently search a space of millions of entries by only looking at a few thousand. However, making this work on actual hardware was a challenge. Unlike dense layers, which are bound by math speed, flops, memory layers are bound by memory bandwidth. Standard PyTorch implementations capped out around 400 gigabytes per second. To fix this, we wrote custom CUDA kernels optimized for atomic additions. This allowed us to hit 3 terabytes per second on H100 GPUs, essentially reaching the physical limit of the hardware. We combined these innovations into an architecture we call Memory Plus. It features a shared memory pool, meaning we reuse the same massive set of parameters across multiple layers of the network. We also introduced specific gating mechanisms and CLU nonlinearities. This ensures that the training remains stable, even as we scale the memory to billions of parameters. To prove this works, we set up a rigorous comparison. We compared our Memory Plus models against two strong baselines. First, standard dense models, like Llama 2 and 3. Second, mixture of experts, MO, models. Crucially, all comparisons were compute-controlled, meaning we ensured our models didn't get an unfair advantage in processing power. The results were striking. On factual benchmarks like TriviaQA, our Memory Plus models, shown here in orange, consistently outperformed both the dense and MO baselines. In fact, our models often matched the performance of dense models that use 2x to 4x more compute. We are getting better results for a fraction of the cost. We also found that the scaling laws hold up. As we add more memory parameters, the x-axis, our accuracy, the y-axis, improves log linearly. Look at the highlight on the right. We found that a small 1.3 billion parameter base model, when equipped with 128 billion memory parameters, could perform as well as a 7 billion parameter dense model. That is a massive efficiency gap. We didn't stop at small models. We tested this on the 8 billion parameter scale. With just 1 trillion tokens of training, our Memory Plus model approached the performance of Llama 3.1, which was trained on 15 trillion tokens. This suggests that memory layers act as a fast lane for knowledge acquisition, allowing models to learn facts significantly faster than dense architectures. Through our ablations, we found an architectural sweet spot. While adding memory helps, we shouldn't replace every layer. We found the global optimum is replacing exactly 3 layers with memory. Beyond that, you start losing the reasoning density of the core model. It is important to distinguish this from mixture of experts. MO routes you to different calculators. Memory layers route you to different filing cabinets. For complex reasoning, MO is great. But for factual retrieval and knowledge-intensive tasks, memory layers are the superior choice. To recap the engineering reality, this is not a free lunch. It requires moving beyond standard abstractions to custom kernels. It requires handling training instability with techniques like QK-norm. It represents a paradigm shift from being compute-bound, waiting on math, to bandwidth-bound, waiting on data. Looking forward, this points us toward the disaggregated model. Imagine a reasoning core that is instruction-tuned, connected to a massive memory full of raw knowledge. This allows us to update facts without retraining the brain, and it helps reduce hallucinations by making retrieval explicit. In summary, memory layers allow us to add billions of parameters without the compute penalty. We have engineered them to run at 3 terabytes per second, and they drastically reduce the training data needed to reach state-of-the-art factuality. This is a production-ready component for the next generation of AI. Thank you.